Two facts from Euclidean geometry that you probably remember are that the shortest path between 2 points in a plane is the straight line joining them, and also the shortest path between a point and a plane is a straight line from the point to the plane meeting it at right angles. In this section we want to understand whether similar statements can be made in Lorentzian geometry. Now there are two reasons why the relationship between geodesics and shortest length paths becomes more complicated outside Euclidean space. Even in a typical Riemannian geometry, the geodesics are minimal length paths between the endpoints only when the endpoints are sufficiently close. Secondly, in a Lorentzian space-time, 2 points that can be joined by a timelike curve can be joined by timelike curves of arbitrarily small length. So there's no point in looking for a minimal length curve. It's actually more natural to look for curves of maximal length. Let's illustrate the first of these in the simple example of a sphere. The sphere is a two-dimensional Riemannian geometry, and its geodesics are great circles, for example, the lines of longitude. So the shortest distance on the sphere between the South Pole and any point is the line of longitude from the South Pole to that point. A curve like this is the shortest distance between its endpoints. That remains true as we push further and further north along our geodesic, until we get to the North Pole. There are, of course, infinitely many curves of the same length joining the South and North Poles together. So our curve, the red one, is no longer the unique such curve. But it is still a curve of minimal length. However, if we push beyond the North Pole, we find that our geodesic is no longer minimal length. And this is how we can make the argument. Firstly, we can already consider another curve with the same length. This is made by taking the blue curve, which is another great circle, from the South Pole to the North Pole, and then tagging on to the red curve for the rest of the way. This clearly has the same length as the one we first thought of. But now we have an additional possibility, because we can go up the blue curve and then branch off at some point, cutting off the corner. This provides a strictly shorter curve from the South Pole to our endpoint. So a geodesic isn't always the minimal length curve between its endpoints. In this instance, of course, we know that there is another curve from the South Pole to the endpoint along a great circle round the back. That's the global minimum of distance between the endpoints. But our construction shows that we can even make small local changes to the curve and still get one of shorter length. So our geodesic is not the global minimum, and it is not even the local minimum of distance among curves with those same endpoints. Now let's turn to Lorentzian geometry. Suppose that we have a timelike curve between 2 points. Let's see how we can make one that is shorter in Lorentzian distance. The first thing to do is to construct a piecewise null curve with the same endpoints. If you like, you can think of this as a photon bouncing backwards and forwards between mirrors. This curve has 0 distance according to Lorentzian geometry, and of course it's not timelike. But we can approximate it to an arbitrarily good degree by a timelike curve, and that timelike curve therefore has quite a small distance. By making the approximation better and better, we can make the proper time along this curve as small as we like. Now these approximating curves clearly involve periods of high acceleration. In fact, the whole construction is really rather like the twin paradox. And they are very far from what a geodesic ought to be. A geodesic is more or less extreme opposite, and for this reason it's more natural to regard a timelike geodesic as being a curve of maximal length. And this is what we will find holds true when we go into the details, at least when the curve has endpoints that are sufficiently close together.